Okay, this is Unit 3, Chapter 4, my favorite chapter, exponentials and logarithms. So let's get started. Question 1, we're graphing a logarithmic function. That was from section 4.3, graphing logarithms. We'll go question by question here. For part A, it says identify the y-intercept. Remember to find the y-intercept of any function. You let x equal 0. So this is going to be a 0 right there for x. So it's 1 plus log base 2. And again, if you put a 0 in there, 0 plus 4, which is 4. And then remember, you can change 4 into 2 squared. And the reason you'd want to do that is now you have matching base. Log base 2 cancels with base 2, leaving the exponent. So this equals 1 plus 2, which is 3. So the y-intercept is 3. State the equation of the asymptote. The thing to remember about logarithmic functions is they have a vertical asymptote. Again, logarithmic functions have a vertical asymptote. Usually it's right here at x equals 0, but there has been a horizontal transformation to the left 4, which moves that vertical asymptote. So the vertical asymptote is there, and the equation is x equals -4. The domain and range of g of x. The graph is going to be contained on the right side here. We're going to have to get a couple more points to get the exact shape of it, but the graph is going to look something like that. And so we can see that the domain starts here at -4 and goes in that direction. And then the range is going to go from -infinity to +infinity. So for part C, we can say that the domain, it doesn't include -4. So I'm going to put a parenthesis, but it goes from -4 to infinity. The range is from -infinity to +infinity. Now we need to sketch the graph. So we already have 1 point on the graph when x equals 0. We got y equals 3. If I plug in now a -2, for example, and I'm not choosing values at random, I want to be able to plug in specific values for x that are going to give me powers of 2 because I have a log base 2. So if I plug in, let me do it down here, log base 2 of -2 for x plus 4. -2 plus 4 turns into 2 to the first power. Log base 2 cancels, so I have 1 plus 1. So 1 plus 1 gives me 2. So when I plugged in -2, I got +2. I can also plug in -3. If I plug in -3 for x, I get -3 plus 4, which is 1. And this is just something that hopefully is familiar to you, and it's something important to remember. Log of any base of 1 is always 0, and then 0 plus 1 is 1. So when we plug in -3, we get 1. And that would be the sketch of the graph. Okay. So now we have an exponential function, 2 to the x. And this now has a horizontal asymptote that's typically at the line y equals 0, unless there's a vertical transformation, which there is. We're moving the graph down 1. So our horizontal asymptote is going to be at -1. So that's good. I'm kind of jumping around here. I apologize, but that answers part B, find the asymptote. It's a horizontal asymptote with an equation of y equals -1. Now here for part A, to find the y-intercept, again, we let x equal 0. So 2 to the 0 plus 2 minus 1. I put in a 0 for x. So 0 plus 2 is 2, 2 squared is 4, and 4 minus 1 is 3. So we plugged in 0 for x, got a 3 for y. Now we need to sketch the graph. So as we did with question 1, I'm going to get a few more points other than the one I have. So I already have the point 0, 3. I'm going to plug in -1 for x. So if I plug in -1, I'm going to get -1 plus 2. And 2 to the first power minus 1 is 1. So -1 comma 1. Okay, so we had -1 comma 1. Now I'm also going to plug in -2 for x. That's going to be 2 to the -2 plus 2 minus 1. -2 plus 2 is 0. 2 to the 0 is 1. 1 minus 1 is 0. So -2 comma 0. And even though it didn't ask specifically for domain and range, which I think is kind of odd because it most likely will be for any graphing problem, the domain of this, it goes from -infinity to +infinity is the domain. And then range goes all the way down to -1, not including -1, and it goes all the way up to +infinity. So -1 to +infinity. All right, solving logarithmic equations, section 4.5. What can't happen here, and this is really important to remember because I see a lot of students fall into this pitfall. Most students remember that it's a base that cancels a logarithm, but you can't use multiple bases like this. This is the mistake I see a lot of students make, trying to cancel two separate logarithms like that. It doesn't work that way. When you exponentiate or when you use a base, you can only use one base on one side of the equation and one base on the other side of the equation. So the first step has to be to condense these two logarithms into one logarithm. So log base 6, and since there's a plus sign between the two logarithms, the expressions inside multiply. So x plus 2 multiplies with x minus 3. Now that we have one single logarithm, I can use a base of 6 on both sides to cancel the logarithm. So we have, and then I'm going to say that equals 6, and I'm also going to multiply those two together, the x plus 2 and the x minus 3. When we multiply that together, we're going to get x squared minus x minus 6. Okay, and then when we subtract the 6, we're going to get x squared minus x minus 12 equals 0. Now there's nothing more than just a quadratic equation, which we have solved a lot of. We can solve it by factoring. And then we get x equals 4, and we get x equals -3. The other common mistake students make regarding logarithmic equations is forgetting that you cannot have a negative value inside of a logarithm. That doesn't mean that your solutions can't be negative. You can have negative solutions. They just can't make the logarithm negative. What I mean by that is a -3, for example. If I plug in a -3 here, -3 plus 2 is -1. You can't take the logarithm of -1. So -3 is what's called an extraneous solution. 4 plus 2 here works. That's 6 here. 4 minus 3 is +1. That works there. So 4 is good. So the only solution would be x equals 4. On the exam, in a situation like this, if you fail to cross out an extraneous solution, you wouldn't be able to get full points on the problem. So just be aware of that. Question 4 is very similar. We have multiple logarithms. So the first step is to combine into one single logarithm. Now we have a subtract or a minus separating the two logarithms. So when we condense two logarithms separated by a minus sign, it's called the quotient property or the quotient rule. So we have to form a quotient, this being the numerator, that being the denominator. And that equals 2. Now that we have one single logarithm, again, we can use a base of 3 to cancel that logarithm, and you have to do the same thing on both sides because it's an equation. So now we have the equation 9 over x plus 2 equals 9. And then it's not fun to solve equations with fractions, so you can clear the fraction by multiplying both sides by the denominator. So now we have 9 equals 9 times x plus 2. We can go ahead and divide by 9 and get 1 equals x plus 2, which gives us a solution of x equals -1. And again, it's not that your solution can't be negative, it just can't make the logarithm negative. So if we plug in a -1 right here for x, -1 plus 2 is +1, which is fine. So x equals -1 is a valid solution. Okay, question 5. It is exponential. It's slightly different than the usual exponential equation that we've been solving. This one resembles more of a quadratic equation in form, and it's solved using the same techniques we would with solving quadratic equations. What I mean by that is e right here, e to the 2x is the same thing as e to the x squared. Instead of thinking of it as e to the 2x, when you have an exponent that's being raised to another exponent, you multiply, and that's where the 2x comes from. The reason you'd want to think about it like this is you can do a trick now called substitution, not the substitution method we learned in with systems of equations and matrices, but variable substitution, more commonly known as U substitution in a calculus course, for example, where you use it a little more heavily. But if I said let u equal e to the x, now I'm going to substitute. Anytime there's an e to the x, I'm going to put a u there. So this could be written as u squared plus 5u minus 6 equals 0. And now we have an equation quadratic in form that we can solve by factoring. So we could say u plus 6 and u minus 1 equals 0. So then our solutions would be u equals -6 and u equals 1. Now we're not solving for u though. Remember, we're solving for x, and now we can go and undo that substitution and say that e to the x equals -6, and over here e to the x equals 1. Now this is not going to have a solution. Reason being, if we were to solve this, we'd have to take a natural log on both sides to cancel the base e, but natural log of -6 doesn't exist. You can't take logarithm of negative values. So this is not going to give us a solution. It's similar to what we did here in problem 3 with extraneous. So that's not going to work, that side of it at least. Over here though, we can solve this one simply by using a logarithm on both sides. a natural log rather, cancels a base e. So x equals the natural log of 1. And if you happen to forget, I've already mentioned it, but anytime you take the logarithm of 1, it equals 0. But luckily, the natural log is one of the logarithms your calculator can do. So if you type in natural log of 1, your calculator is going to tell you the answer is 0. Okay. Now, question 6. This is one of those applications of exponentials. And it is saying that it's compounding continuously, and then it gives two different interest formulas. And you're supposed to choose, and the key word is compounding continuously, is this formula here, PERT. This formula is used when it's compounding at regular intervals like monthly or quarterly or annually. So it's up to us to figure out first which equation to use, and it's the continuously compounding one, which is this one. So use future amount A is equal to principal amount times E, the rate times time. And the question is, how long will it take? So let's solve for t. That's a question of time. Solve for t when r equals 0.07, when the principal investment is 8,000 and the future amount is 20,000. And then we solve for t. So 20,000 is equal to 8,000 times e to the 0.07 times t. We would divide by 8,000 as a first step. So divide by 8,000. And then the 3 zeros cancel. 20 divided by 8 is 5/2. And then we need to get this exponent, 0.07t. In order to solve for t, it can't be an exponent, so we need to cancel the base e, and that's going to take the natural log on both sides. Natural log. So now we have the natural log of 5/2 equals 0.07 times t. And then if we divide by 0.07, that solves. And then you can get your calculator out and do natural log 5/2 divided by 0.07. We get 13.1. So it takes 13.1 years at that interest rate, compounded continuously for 8,000 to grow to 20,000. Okay, question 7, they've given us a model. It's the average cost of a house where C of t is measured in thousands of dollars. Estimate the average cost of a house in 2010. So 2010 is a measurement of time, okay? But it says that t is the number of years after 2000. So 2010 means that t equals 10 years because it's 10 years after the year 2000. So for part A, it would just be 100 plus 25e to 0.03. You plug in a 10. For t, we have 100 plus 25e. 10 times 0.03 is just 0.3. So I need 100 plus 25 times e to the 0.3. It's 133.7. Excuse me. And that's in thousands of dollars. So it's 133.7 in thousands of dollars. So $133,000. So according to this model, when will the average cost of a house in some town, USA, reach 250,000? And so the pitfall students can make here is, first of all, not knowing where to plug in this value. Now 250,000 is the cost, so it's going to plug in for C of t, but C of t is measured in thousands of dollars already, so 250,000 means that for part B, you let C of t equal 250, because C of t is already measured in thousands of dollars, so it's 250. So we're going to solve the equation 250 equals 100 e to the 0.03 t. And we're going to have to solve for t. So first of all, it would help if I wrote this equation right. 100 plus 25 e to the 0.03 t. There we go. So subtract 100. That's 150 plus 25 e to the 0.03 t. Now divide by 25. 150 divided by 25 is 6. So now we have 6 equals e to the 0.03 t after dividing by 25. Now we need to solve for t. In order to do that, we have to cancel the base, and a base e is canceled using a natural log, so use a natural log on both sides. So this gives us natural log of 6 equals 0.03 t. And then divide by 0.03. And t is equal to the natural log of 6 divided by 0.03. So natural log of 6 divided by 0.03 is 59.7. And since t is a measurement of time, it's 59.7 years after the year 2000, so 2059 is when the average house cost would reach 250,000. Okay, question 8. On a cold winter temperature, turn-off is given by. So we have two values of t. Big capital T is the temperature, and t, little t, is minutes. Find the temperature of the engine. So that's finding big T. So find capital T when little t equals 20. So natural log of t minus 20 over 200 equals negative 0.11. And then this is where we plug in the 20 right here for little t. So we need 20 times negative 0.11 negative 0.22, or rather negative 2.2, sorry. Now we're solving for big T, capital T, which is inside of a logarithm. And you can't solve for variables if they're inside of a logarithm, so we need to cancel a logarithm, and we know what cancels logarithms. It's a base that cancels a logarithm, and if we have natural log, then we're going to use a base e on both sides. A base e cancels the natural log, so we have t minus 20 over 200 equals e, so negative 2.2. Then we can multiply both sides by 200 to cancel the denominator, or clear the fraction. So t minus 20 equals 200 times e, so negative 2.2. And then we can add 20. So the temperature is going to be found from this expression, 200 times e to the negative 2.2 plus 20. So let's see what that is. 200 times e to the negative 2.2 plus 20 is 42.16. And that's degrees, what is it, Celsius? It doesn't say. Typically in these scientific-based problems, it's in Celsius, but it's 42.16 degrees. And that'll do it for Unit 3, Chapter 4, Logarithms, Exponentials. Again, key components here that we reviewed are graphing logarithmic functions and exponential functions. Remember, with logarithmic functions, you have a vertical asymptote. With exponential functions, you have a horizontal asymptote. You need to find 3 values with each of those 3 points to graph. And probably the largest portion of Chapter 4 was solving equations, solving logarithmic equations, solving exponential equations, and that transfers over to the problems that we just did, doing applications of logarithms and exponentials, which is basically solving logarithmic and exponential equations. So very important to review solving equations, logarithms, and exponentials.